Hello, the purpose of this video is to introduce you to the concept of absolute value on the real line. So this is section 2.2, absolute value. And the real line. Okay, so the plan for us is twofold. We will talk about the definition and properties of the absolute value. And two, we'll talk about the real line, and we will define the concept of a neighborhood. And this is a central concept for us, which will keep reoccurring. So give this concept of neighborhood a special attention. Okay, so definition. What is an absolute value? So by definition, the absolute value of a real number A is denoted by A, and it's defined as being equal to A. If A is positive, it's going to be equal to 0 if A is 0, and it's going to be equal to negative A if A is less than 0. There's an alternative definition which is quite helpful, and for this definition, one will define the absolute value as being equal to the maximum of the set containing negative A and A. So whatever is this set which contains two elements, A and its opposites, we take its maximum. So I suppose everybody is pretty comfortable with these concepts. For example, the absolute value of 5 is 5, and the absolute value of negative 5, it's the larger number in between negative 5 and its opposite, which is 5, so it's going to be 5. Okay, and perhaps another way for us another way for us to think of what the absolute value of A is to think of the absolute value of A as being equal to the distance from A to 0. So let's say it's the distance between A, it's the distance between A and 0. And perhaps this picture here is helpful. If this is 0 and this is A, then if you compute the distance between 0 and A, whatever this number is going to be a positive number, right? And that's the absolute value of A. It's also possible to take a number which is which I suppose is negative. So suppose B is negative, and if you compute the distance between B and 0, although B is negative, the distance between B and 0 is a positive number, and this is the absolute value of B. Okay, so there are 8 main important properties regarding the absolute value. The first property tells us that the product of the absolute value of a product is a product of absolute value. Secondly, the square of the absolute value of a is equal to a squared. Thirdly, if the absolute value of a is less or equal to c, if and only if negative c is less or equal to a, which is less or equal to c. Fourthly, the opposite of the absolute value of a is less than or equal to a, which is less than or equal to the absolute value of a. And the triangular inequality, which is probably the most important property listed here, tells us that the absolute value of a plus b is less or equal to the absolute value of a plus the absolute value of b. And I'm going to ask you to keep to pay extra attention to the triangular inequality because it is ubiquitous, and as you'll see, it will keep reoccurring over and over. And then there's a generalized triangular inequality, which is an extension of the triangular inequality, which says that the absolute value of a sum of n elements is less than the sum of their absolute values. Next, the absolute value of an absolute value of difference of the type absolute value of a minus absolute value of b is less than the absolute value of the difference. And finally, the absolute value of a difference is less or equal to the sum of the absolute values. Alright, so let's get started on the proof of these properties. So the first one, so for the first one, assume that a and b are two positive numbers, so a and b is in P. Then by the closure of the set of all positive numbers on the multiplication, then a times b will be in P. Hence, the absolute value of a and b will be equal to itself, be equal to AB, and because A is positive, the absolute value of A is A, and because B is positive, the absolute value of B is B. Since A is equal to its absolute value and B is equal to its absolute value. Okay, so now assume that either A or B is equal to 0, then clearly, then A times B will be equal to, the absolute value of A times B will be equal to 0, which is the product of the absolute value. Now, if both A and B are negative, then the product AB will be in P. Hence, the absolute value of A and B will be equal to AB, which is then 1 times AB, which is negative 1 squared times AB, which we can then write as negative 1 times A times negative 1 times B, and that will be equal to negative A times negative B, and this is going to be, we know that this here is equal to the absolute value of A because A is negative, and this will be equal to the absolute value of B, so we get A times B. Alright, so if 1 is positive and the other is negative, let's say A is positive and somehow B is negative, then clearly AB will be less than 0. Hence, the absolute value of A and B will be equal to the opposites of the product, which is negative A times AB, which is A times negative B, which is the absolute value of A times the absolute value of B, because B is negative and the opposite of B is the absolute value of A and B. Alright, So this takes care of our first claim. Now regarding our second claim, which, to remind you what it is, we want to prove here. So for part 2, we want to show that the absolute value of a square is equal to a square for any real number a. Alright, so to this case, so first we observe that the case where a is equal to 0 is obvious, and I will not waste your time with that case. So let us assume then that a is positive, that is, the absolute value of a is equal to a, and the square of the absolute value of a is of course the product of these two numbers, which will be then a times a, which is equal to a squared. Okay. All right. So assume for the third case that a is negative, that is, that the absolute value of a is the opposite of a, and the square of the absolute value of a is negative a times negative a, which you can write then as negative 1 times a times negative 1 times a, which is then negative 1 square times a square, which is 1 times a square, which is equal to a square, which is the desired result. All right. So moving forward, let's prove number 3. And number 3 is the following. So we want to prove. Next, we want to show that given c, which is greater than 0, the absolute value of a is less or equal to c, if and only if negative c is less or equal to a, which is less or equal to the absolute value of c. Okay, so again, there are 3 cases to look at here. So let us assume that the absolute value of a is less than equal to c, and c is some positive number. Then for the first case 1, notice that if a is 0, then clearly the absolute value of a will be 0, and of course 0 is less or equal to c. Okay, for the second case, if a is positive, assume that a is a positive number, then the absolute value of a is itself a, and clearly a is less or equal to c, right? Because we can replace this quantity here by a. And then case 3, assume that a is less than 0, then the absolute value of a is the opposite of a, and replacing the absolute value of a with the opposite of a, we get that negative a is less or equal to c, which implies that a is greater or equal to the opposite of c. Thus, if the absolute value of a is less than or equal to c, then negative c is less than equal to a, which is less than or equal to C. So now we have proved one direction. Now it remains to prove the other way around. So next, it remains to show that if negative C is less than A, which is less than C, then if the absolute value of A will be less or equal to C. And I will leave this as an exercise. This is left as an exercise. And essentially all you have to do here is rehash the previous technique, and you should be able to derive that. All right, so next we want to show that this is true. A is sitting in between the negative of its absolute value and its absolute value. That's the fourth part of the proof. So again, there's several cases. If you assume that A is equal to 0, then clearly the inequality holds. And if we assume that A is positive, then the absolute value of A is going to be equal to A. And in this case, we know that the opposite of A, right, is going to be negative. So it's less or equal to A, which is a positive number, which is of course equal to itself. So we get what we need. And if you assume that A is less than 0, then the absolute value of A is the opposite of A, and A here is now a negative number, right? So it's of course equal to itself, so it's less than or equal to itself, which is then less or equal to negative A, since negative A is a positive number in this case. So we have exhausted all possibilities. So in summary, we have that for any real number A, this is what I mean, this holds true. Okay. All right. So next, I will establish the triangle inequality. Remember that the triangle inequality states that for any real number A and B, the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Okay. All right. So this is a place where I'm going to the one of the alternative definition that I gave you is pretty useful. So recall that we have said that the absolute value of A plus B is in fact the maximum of the set containing A plus B and the opposite of that. All right, so we need to prove here. So we need to prove that the maximum of the set containing A plus B is less or equal to this quantity, and it suffices here. So I suppose it suffices to prove two things. Let me write what it suffices to prove here. So it suffices to prove that A plus B is less or equal to this quantity, and negative A minus B is less or equal to A plus absolute value of A plus B, right? Because now the maximum of these two numbers is the absolute value of a plus b. So if I can show that these two numbers are less than or equal to the sum of the absolute value of a and b, then of course the maximum will also follow the same, will satisfy the same inequality, and therefore the claim would be true. Now, according to part 4, according to number 4, we already know that a is less than or equal to its absolute value, and we know that b is less than or equal to its absolute value. Now, by adding these inequalities, we derive that a plus b is less or equal to the absolute value of a plus the absolute value of b. So this takes care of half of what we need. Now let's look at the other half. We also know that negative a is less or equal to the absolute value of the opposite of a, and negative b is less or equal to this. Again, adding these two inequalities together, then we get that negative a minus b is less or equal to the absolute value of a plus the absolute value of b. So thus the absolute value of a plus b, which is the maximum of a plus b and negative a minus b, is less than this sum here, and this is the desired result. The part 6, which is the generalized triangular inequality, is essentially obtained by induction. So for number 6, which is the following, given a1, a2 all the way till an, is less than is. This is what we want to show. This is the claim, and so for the proof will be by induction, and the base case follows from this is for every natural number. Forgot to say that here. For every natural number, and okay, so let's say that's okay. So for the base case follows from the fact that the absolute value of a1 is actually equal to the absolute value of a1. All right, so there's really is nothing to prove here. Now, for the inductive step, let us assume that a1 plus a2 plus plus ak is less or equal to this plus ak for some natural number k greater or equal to 1, then we know that so a1 plus a2 plus plus ak plus 1, we can rewrite this as, notice, this can be rewritten as this sum here, a1 plus a2 plus plus ak, right, and plus ak plus 1, and you can think of this first, you can think of this as being x, and you can think of this as being y, And by the triangular inequality, we know that this will be less than, this will be less or equal to a1 plus a2 plus plus ak plus ak plus 1 by the triangle inequality. And then by assumption, this is less than plus a2 plus plus the absolute value of ak plus ak plus absolute value of ak plus 1. This is by the inductive hypothesis. And this gives us the desired result. Therefore, the result holds. We can now say it's now safe to assert that given a1, a2, all the way till an, the absolute value of the sum of those numbers is equal to the sum of the absolute value for every natural number n. All right. So next, I will like to prove the seventh result, which is stated as follows. So let me remind you, the seventh claim is that given a and b, two real numbers, this inequality holds true. Okay. All right. So to proceed, we'll use again the max definition of the absolute value. So for the proof, recall that the absolute value, this quantity of this difference, is in fact the maximum of the sets containing this quantity and its opposite. And so now we need to show here, we need to prove that two things hold and also holds. Okay, so here's the idea. So if we write the absolute value of n, this is a good trick for you to remember, because you'll get to use this kind of trick a lot. We can write the absolute value of a as a plus 0, and we can write 0 as let's say we can write 0 as negative b plus b, and then by the triangular inequality, this is the absolute value of a minus b plus the absolute value of b, and this is the last, this step here is due to the triangular inequality. By the triangle inequality. All right, and then so the absolute value of a minus the absolute value of b is then less or equal to the absolute value of a minus b. And we'll play the same game with b. You take b, and then we rewrite the absolute value of b as the absolute value of b plus 0, which is the absolute value of b minus a plus a, again, which is less than or equal to b minus a plus the absolute value of a. And again, this inequality here is by the triangle inequality. And then we'll get that you get that this inequality holds, but this is the same thing as the absolute value of a minus b. So if we call this here star and we call this double star. Since star and double star hold, then the maximum of a absolute value of a minus b and the absolute value of b minus the absolute value of a, which is the absolute value of this difference here, must then be less than that. And that gives us exactly what we need. And finally, I'd like to prove the last result, which is the following claim. Given a and b, two real numbers, the absolute value of this difference is less or equal to the sum of the absolute value of a and b. All right, so what is the strategy here? So again, we'll recall, so for the proof, we recall that the absolute value of a minus b is the maximum of the set containing a minus b and b minus a. All right, so then we know that a is less or equal to the absolute value of a, and b is less or equal to the absolute value of negative b, and these together imply that if we add these inequalities together, we get that a minus b is less or equal to this sum, which is this here. Again, similarly, b is less or equal to its absolute value, and negative a is less or equal to its absolute value, and together these two inequality imply that adding this inequality together we get b minus a is less or equal to b minus the absolute value of a. I'm sorry, plus minus here, which is absolute value of a plus b, and this gives us exactly what we need. Okay. All right, so let's look at an exercise here. Suppose we are interested in solving the inequality 2x, absolute value of 2x plus 3 is less than 7. All right, so recall from what we've seen, we know that 2x, absolute value of 2x plus 3 is less than 7 is equivalent to negative 7 is less than 2x plus 3, which is less than 7. Okay, and then okay, this should be pretty straightforward from there. So then we get that negative 7 minus 3 is less than 2x, which is less than 7 minus 3, which is then negative 10 is less than 2x, which is less than 4, and then dividing this inequality by 2, we get that negative 5 is less than x, which is less than 2. So we can then say that 2x plus 3 is less than 7 if and only if x belongs to the open interval negative 5 to 2. Okay, easy enough. So next, let's look at the following inequality. Absolute value of x minus 1 is less than the absolute value of x. And I will, to help myself solve this inequality, I'll make a table. Have x here, let's say negative infinity to infinity. Let's look at the 0 for x minus 1 is 1, the 0 for x is 0, so we have two zeros. X is 0 when x is 0, x minus 1 is 0 when x is 1, We order the zeros from smaller to larger. And let's look at the sign of x minus 1. X minus 1 would be 0 here, and then it's negative at the left of 1, positive at the right of 1, right? So when x is bigger than 1, x minus 1 is positive. And what happened to x? Well, x is going to be 0 when x is 0. It's negative here and then positive and there and so on. Now the absolute value of x is going to be 0, of course, when x is 0. It's going to be the opposite of x when x is negative, and it's going to be equal to x whenever x is positive. And the absolute value of x minus 1 is going to be 0 when x is 1, and is going to be equal to the opposite of x minus 1 when x minus 1 is negative. So in this interval here, we should get negative x plus 1. Here, we should also get negative x plus 1. And then here, we should get just x minus 1. So, there are 3 cases to look at here, right? So for the first case, case 1, if x is in between negative infinity and 0, then the inequality x minus 1 is less than the absolute value of x is equivalent to negative x plus 1 is less than x. And then adding things, so if I move, I'm sorry, this should be negative x here, okay. Alright, so then if I move the negative x here, then we get 1 is less than 0, which is false. So we have no solution if the inequality has no solution if we assume that x is less than or equal to 0. So case 2, let us suppose that x is in between 0 and 1. Then in this case, our inequality, right? So here we are really in this scenario here. We are in this scenario. Particularly, we have to pay attention to this part here. Right, so our inequality becomes equivalent to negative x plus 1 is less than x, which is equivalent to 1 is less than 2x, which really is equivalent to 1/2 is less than x, or x is greater than 1/2. And so in this case, the solution set here is that x is an element of 1/2 1. All right, so it remains to look at the third case. So let me see if I can make some room here for that. Case 3. In this case, x is greater than 1, and we are in this situation. Let me highlight that. We are here. And our inequality then here is now equivalent to x minus 1 is less than x, and this is equivalent to negative 1 is less than 0, which is of course true. So the solution is the entire set here, the universal set here, which is x is in between 1 and infinity. All right, so they are so summarizing what our finding, we have in the first case no solution. In the second case, when x is in between 0 and 1, we have this, and then finally we have that. So if I had to highlight where we have a solution, if I put half here, so will be all of this, and of course we will have to exclude 1/2, right? Okay, so in summary, if I were to So in conclusion, we have that the absolute value of x minus 1 is less than x if and only if x is in between 1/2 and infinity. So x is strictly bigger than 1/2. Alright, so moving forward, let's talk about the real line. So with the real line, let's say the real line is the following line, by which we represent R. We have the real line, you have 0 here, negative infinity there, infinity. We say that these are the negatives, and these here are the positive numbers. And so remember that we can now endow the set of real numbers with a metric system. We can in fact measure the distance between two numbers. If you give me A and B here, and I want to understand how far apart these two numbers are, then we can now say that the distance between A and B is the absolute value of A minus B. So if you think about, if you stop for a second and think about everything that we've done so far, we have endowed the set of real numbers with three structures. We had an algebraic structure which was given to us by a set of axioms, algebraic axioms, and related to multiplication and addition. And then after that, we have endowed the set of real numbers with an ordering structure by imposing by providing a set of assumptions which we call the ordering axiom. We had three of those, and then now we have a metric structure. We have a way to capture the distance between two real numbers, and this is given to us by the absolute value. If I want to measure how far two numbers are from each other, I compute the absolute value of the difference. All right, next, we'll look at the concept of a neighborhood. If we let A be a real number, and let's suppose that epsilon is an arbitrarily chosen positive number, we call an epsilon neighborhood of A, and we denote this by, and we denote by V sub epsilon of A. It's simply the interval A minus epsilon, A plus epsilon. So what is the idea here? Pick a number A, any number A on the real line, and fix some epsilon, which is a positive number. So let's say, for example, here, suppose that epsilon is equal to 1. Then this will be A minus 1, and this point here is A plus 1. And so you can see that the distance between these two is 1, and the distance between these two is also 1, for example. This is just an example. And this neighborhood, this open interval, which is a minus 1 to a plus 1, this is a one neighborhood of a. Okay, so more generally what we have is the following. If you have a here and then you have some epsilon, which is a positive number, so this is now a minus epsilon. Epsilon is any positive number which is fixed, and then you have a plus epsilon, and we consider this neighborhood. This is V epsilon neighborhood of A. That's A minus epsilon to A plus epsilon. Right, so that's the definition of an epsilon neighborhood of A. It's like a bubble around A of radius epsilon. Alright, so now I remark the following. 1. X is in an epsilon neighborhood of A if and only if the distance between X and A is less than epsilon. And this is the same thing as saying that the absolute value of the difference X minus A is less than epsilon. Same thing. So this set here, an epsilon neighborhood around A, is a collection of real numbers such that the distance between X and A is less than epsilon. And 2, later we will be interested in a very small neighborhoods of the form V epsilon A. And the next theorem that I will introduce is called the infinitesimal phenomenon theorem. The infinitesimal phenomenon, and this theorem is stated as follows: let A be a real number, then there exists X in an epsilon neighborhood. There exists X in an epsilon neighborhood of A. There exists an epsilon neighborhood around A, such that for every epsilon greater than 0, then X is equal to A. I suppose if there exists, this is important. Should put if there exists. So if you let A be a real number, so let me draw a picture here. And and you pick any epsilon neighborhood around. So suppose this is some epsilon neighborhood around A, and you can find that exists an X which is here, right? So no matter how small a neighborhood around A is, your X is always inside that bubble. So if I can draw another picture maybe here, and I draw even a smaller neighborhood around, then X is located right there. So this theorem says that if you can find such an x which is inside every epsilon neighborhood of A for every epsilon, then in fact x must be equal to A. Alright. So let's try to establish this theorem. Let us suppose let's A be a real number and assume that there exists an x which is inside an epsilon neighborhood of A for all epsilon which are positive. Okay, so then this is equivalent. This is equivalent to the following statement. The absolute value of x minus A is less than epsilon for every epsilon which is positive. And this is equivalent to the absolute value of x minus A is equal to 0. And this is in fact coming from, I believe we have proved results similar to this, but this is coming from theorem 2.1.9. But the fact that the absolute value of x minus A is equal to 0 tells us that x minus A must be 0, which then tells us that x must be equal to A. Okay, so the only number which is inside any epsilon neighborhood of A is A itself.